Good evening, everybody. How you guys doing today? You doing well? Yeah. My name is Patrick Justice, and I'm the Program Assessment Intern for the Office of Campus Life and Dean of Students. It is my great pleasure to introduce you guys to the Last Lecture Series. This is the third installment of Last Lecture Series, where we invite professors to come to speak to students on a one-on-one basis on a topic of their own choosing, as if it their last time speaking in academia. We started this lecture series in memory of Randy Pausch, a professor working at Carnegie Mellon University, who started the series to pass on some final words to his children and students. We've invited very top academics from schools such as Faye Crosby from Cal. We've invited Jody Green, and tonight we have our own Randa Roland from chemistry. So without further ado, I'd like to introduce our Campus Life Ambassador, who's going to introduce Randa Roland, and have a great night. I'm really excited.
Hi. So I have a bad chemistry joke. It's like a lit major. So, just to lighten the mood a little. I was going to make a good chemistry joke, but all the good jokes are gone. So my name is Mariela Glazer, and I'm here to introduce Professor Randa Roland. So Professor Roland has been a dedicated part of Santa Cruz higher education system for a while. She earned her PhD on this campus under the guidance of Professor Robert Anderson. She has taught at Cabrillo Community College, and for the last 9 years, she has been a well-respected full-time lecturer at UCSC. Let's see. She's devoted to the subject of chemistry and her work of teaching, and she says she does not teach for awards. Because I'm not Professor Roland, I can boast for her, and I can discreetly tell you that she has an honorable mention in teaching excellence for the years of 2007 and 2008. I can mention that she has won the Teaching Excellence Award in Physical and Biological Sciences in 2010 and 2011. And perhaps I can also mention that the PRC has awarded her in 2010 for Universal Instruction and Teaching, and then again in 2011 for creating an inclusive campus community. So without further ado, proud cat owner, motorcycle and tattoo enthusiast, your favorite chemistry teacher, Professor Randa Roland.
Thank you guys for coming tonight. This is a little different than my usual lecture format. It's a little more rigid, so bear with me as I try to do more than one thing at once. Thank you for inviting me to participate too. Thank you, the Dean of the Students Office. It's very kind of you. I'm hoping this is not my last lecture, but I'm going to take my last lecture to mean that I'm very old, I'm white-haired, and I'm retiring versus moderately old, semi-brown-haired, and dying. I really do hate the thought of not teaching here at UCSC. It's my dream job, and I love it, and a large part of that is you guys, the students, who make it really special, and the faculty and the staff. I do teach chemistry, and I know that scares a lot of people, so I'm just fine for this. And I know your eyes look for exits, and your stomachs kind of drop, but I promise there's no quiz at the end of this tonight. And I'm not going to try and terrify you or bore you tonight, but I'm hoping that maybe I'll inspire you by telling you a story about chemistry that I find really interesting. But I find most of chemistry interesting anyway. I love chemistry. I see it everywhere. I look at life through like a chemical lens. So, you know, you take a drink of water, and I picture all the little water molecules going down my throat. And, you know, I'd say screaming, but that doesn't. Whoops. Whoa.
You just gotta focus.
You know, but I'll say screaming with delight because nobody wants to think about tortured water molecules. You know, the wind hits my face, sodium, that would be nice. Nitrogen and oxygen hitting my face, bang, 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 you know, or table salt, you've got that nasty chlorine atom pulling the electron away from poor little sodium. You know, that's how I view the world. So it's weird, but I look at atoms and molecules like little people. They have unique personalities and they all have their quirks, and it just makes chemistry come alive. My passion for chemistry has moved beyond the traditional realm into tattoos. All of my tattoos except one are chemistry related. I started with my name and chemical element symbols at the bottom of my back, and it kind of just expanded to take up the whole back, and then started leg, arms. So always waiting for my next one. They draw a lot of attention, so let me just mention a few that kind of also illustrate my message tonight. My ink actually it opens up conversations with a lot of different kinds of people. But you know, we can talk about chemistry and they don't even know that they're getting a chemistry lesson. They don't open a book, and I kind of hope that when they walk away, they might actually want to open a chemistry book. If nothing else, hopefully when they see how passionate I am about it, they start thinking about, well, what do I feel that way about? What would my tattoo be if I wanted to show what I love? Hopefully, and hopefully no parents get unhappy about it. I've committed my life to chemistry, and I have spellicules. One of them is the molecule I'm actually talking about tonight. I have my ode to alchemy, my tribute to candle flame, but the ones that get the most comments are my plants. So each of the 6 plants I have on me, they contain molecules of death, basically. They're these beautiful plants, but they can kill you. So I have, I'll just take a minute. It's always fun to talk about these. I can't do it in a normal lecture, so foxglove over here contains digoxin and digitoxin. Hopefully Rebecca will say that those structures are right. She teaches organic chemistry. So. In the right dose, these can increase cardiac output, and in the wrong dose, they give you cardiac arrhythmias and you die. So, here we have strychnine, and in low doses, very low doses, it can act as a stimulant, and there have actually been athletes that have used it to enhance their performance. I wouldn't want to risk that, but they did. In the wrong dose, you get muscle convulsions, and guess what? You die. You asphyxiate with this one, though, so, you know, a little different. Aconitine, which is down here, is found in aconitum plants like monkshood and wolfsbane. So these are on one side here. This has been called the queen mother of poisons, to kind of pair up with arsenic, the king of poisons. But this is one of the oldest known poisons. It has found some anecdotal use as an antipyretic and an analgesic, but the line is just razor thin between therapeutic and toxic. And when I looked up the symptoms of aconitum or aconitine poisoning, it was this list that would take just pages and pages and pages, and none of them were good. But eventually, you usually die because you have respiratory paralysis or you have cardiac arrest. I just think it's neat though, these beautiful plants, right? And then they contain these horrible toxins. Nightshade, here, this is woody nightshade. It contains a number of alkaloids like atropine and scopolamine. Again, I'm hoping the structures are right. And a mnemonic that I found to describe the symptoms of nightshade ingestion, I'll make sure I get this right, is hot as a hair, light as a bath, dry as a beet, dry as a bone, red as a beet, mad as a hatter. So I'm not sure, I don't think any of those sound very good, but a lot of times you don't die from nightshade poisoning though, which is kind of nice. You may end up waking up naked in an emergency room somewhere, but you might not die. Hemlock, that's this one, contains also alkaloids that cause paralysis. You guys may know the hemlock, the Socrates poison. Eventually, you can't breathe because your lungs get, your breathing apparatus gets, my hands down. It stops working, but your mind stays aware the whole time, so that would kind of suck. And my poor husband here, Don, he worries a lot about my fascination with poisons, but we can talk about that some other time. But all of these molecules highlight the importance of the intention behind an act. Are you using this chemical or this compound for a good reason, or are you using it for a bad reason, like to kill somebody? Another slide here. Again, I'm not used to this, so I apologize. Chemicals and chemistry compounds are not good or bad. It's how you use them, right? It's all about, I think every molecule is beautiful, but when people take them and use them for bad purposes or in the wrong place, then that's when they get the connotation of being bad or that kind of thing. So that's chemistry. But chemistry is really a science of creation and innovation. It's able to solve problems not just in a lab setting, but on a global scale. So my story tonight is really about chemistry and the power of intention. So hopefully when you leave tonight, you'll think about, you might ask yourself, what is my passion and what can I do to make the world a better place? Have good intentions versus bad. Okay. Let's see here. I'm missing a page. I apologize. I'm not fascinated with death, by the way, but it's kind of starting to feel that way. How many of you know what the Haber-Bosch process is? If you've taken general chemistry, you probably do know because it's in every general chemistry book. I can describe it as a method to make ammonia from its elements, nitrogen and hydrogen. But that's a deceptively simple description of a chemical process that changed our world. Can put it another way. Did you eat today? Yeah, you did. Thank the Haber-Bosch process. Why is this one of my favorite chemical stories? It's probably the greatest example of lab-scale chemistry being translated into giant industrial viability. That is no small feat, to take a little reaction and make it work to produce thousands and millions of pounds of some compound every year. It was a feat of chemical innovation, chemical investigation, and then an engineering marvel, really. It was one of the first great marriages of science and technology, and it saves billions of people every day, every day. Succinctly stated, population is capped by resources, and one of the most important resources out there is food. Particularly back when this was developed at the beginning of the 1900s, there was a concern about having enough to eat. If every arable acre on this planet was farmed using the best practices of the late 1800s, we could probably support 4 billion people. The last time I looked, the population of the Earth was over 7.3 billion. So those 3 billion people would be dead. That's 40%, essentially. The Haber-Bosch process keeps them alive. Let me give you a little background for the story, and I apologize for having to read this quote, but it's not too long, but I gotta get the words right. In 1798, Thomas Malthus published an essay on the principle of population, in which he wrote, "The power of population is so superior to the power of the earth to produce subsistence for man, the premature death must in some shape or other visit the human race. Gigantic, inevitable famine stalks in the rear, and with one mighty blow levels the population with the food of the world. The great law of necessity, which prevents population from increasing in any country beyond the food which it can either produce or acquire, is a law so open to our view that we cannot for a moment doubt it." Now, I think Thomas Malthus was an economist, and now I know why we call economics the dismal science. That's a very depressing statement. Throughout the 1800s, the number of mouths to feed was growing. We had advances in water systems, in medical care, in sanitation, antiseptics. but we could only support so many people. There was only so much farmland, and refarming that land dropped its usefulness. Farmers would extend the fertility of their lands by doing crop rotation, having fallow periods, and they also applied manures and compost to redo the nutrients in the soil. It wasn't enough. Malthus's prophecy was echoed by the incoming president of the British Academy of Sciences in his 1898 inaugural address. Some of you may have heard of Sir William Crookes, inventor of the Crookes tube, which is a precursor to cathode ray tubes, which were in old televisions. Oh, right, sorry. This whole thing is, here's my Thomas Malthus slide. I forgot to put him in. He's a happy guy. Here's Sir William Crookes. He also discovered thallium. He was a pioneer in spectroscopy. And again, I did paraphrase his words a little bit, but all of them are important, so bear with me here. He said, "My chief subject is of interest to the whole world, to every race, to every human being. It is of urgent importance today, and it is a life and death question for generations to come. I mean the question of food supply. Many of my statements you may think are of the alarmist order. Certainly they are depressing, but they are founded on stubborn facts. They show that England and all civilized nations stand in deadly peril of not having enough to eat. After wearying you with a survey of the universal dearth to come, I hope to point a way out of the dilemma." So there's a bit of hope there, unlike Malthus. Here's who he thought could fix the problem. It is the chemist who must come to the rescue of the threatened communities. It is through the laboratory that starvation may ultimately be turned to plenty. And he even had a pathway for his fellow chemists to try. There is a gleam of light amid this darkness of despondency. In its free state, nitrogen is one of the most abundant and pervading bodies on the face of the earth. The fixation of atmospheric nitrogen, therefore, is one of the great discoveries awaiting the ingenuity of chemists. This unfulfilled problem, which has so far eluded the strenuous attempts of those who have tried to wrest the secret from nature, differs materially from other chemical discoveries, here's a joke, which are in the air, so to speak, but are not yet matured. The fixation of nitrogen is vital to the progress of civilized humanity. Not quite such a downer as Malthus, but still a little dismal. Without some kind of breakthrough, Crookes actually predicted that humans would begin dying by the 1930s. The creation of vast amounts of chemical manures, synthetic fertilizers, was in his mind the greatest challenge of their time. And by vast amounts, I mean thousands of tons per year. Tons. Plants need nitrogen, phosphorus, and potassium. NPK fertilizers, you see that on some of the bags of fertilizers. From the 1840s up till the present day, there have been enough natural deposits of phosphate rock and potash to meet the phosphorus and potassium demand. Nitrogen is the problematic one. It's a requirement for both plants and animals. Nitrogen is the fourth most abundant element in our bodies after carbon, hydrogen, and oxygen, but is the hardest to get from nature in a usable form. Amino acids contain nitrogen, and they're the building blocks of proteins. And enzymes are proteins, by the way. Nucleic acids contain nitrogen, and they're the building blocks of DNA and RNA. Proteins, DNA, RNA, these are molecules of life, at least as we know it. Crookes mentioned fixed nitrogen, which is chemically available nitrogen. Compounds like ammonia, ammonium sulfate, urea, potassium nitrate, sodium nitrate, and ammonium nitrate, these are examples of fixed nitrogen. We're swimming in nitrogen right now. About 78% of the atmosphere is dinitrogen, atmospheric nitrogen, or N2. That is not fixed. It has very low bioavailability. We can't use it the way it is. Now, A lot of you know that breaking a chemical bond requires an input of energy. So the unit we usually use as chemists is joule or kilojoule. So to give you an idea of what a kilojoule is, 0.3 kilojoules is a lethal dose of X-rays. The kinetic energy of a bullet fired from an M16 rifle is about 2 kilojoules worth of energy. In atmospheric nitrogen, dinitrogen, those two nitrogen atoms are locked together in a covalent bond that is the second strongest covalent bond in nature, probably the least reactive. It has a bond energy of 945 kilojoules per mole. Just so you can see what a mole of gas is, I have my mole box. If you condense that liquid nitrogen into the liquid form, which is really cold, 1 mole would occupy about 35 milliliters, which is not very much at all. If we have time, we'll play with our liquid nitrogen. Anyway, makes the best ice cream. Somebody asked me if I was going to make beer with it. I haven't quite figured out how that works. To break that nitrogen-nitrogen triple bond just with heat thermally, it takes over 1,000 degrees Celsius to do that, which is about 1,800 degrees Fahrenheit. Sorry for the F word, but we still think of Fahrenheit. That dinitrogen bond is a monster. Tragically, nitrogen is a necessary component for molecules that are important in agriculture, industry, and life. And I'd say ammonia is the starting material for almost every synthetic nitrogen compound out there. So, very important. I am not an expert on microorganisms, so I hope I will not say anything wrong. Nitrogen fixation does occur in nature. It's insufficient to meet human demand, but it's out there. 2 main groups of microorganisms carry out nitrogen fixation, and they do more than 90% of the fixation that does occur in nature. The more common of the 2 groups is made up of microorganisms that live in the soil and the water, free-living diazotrophs. A few types of bacteria. I have some, I guess I can point at it, but that's weird. I have some green sulfur bacteria, some azotobacteria, and some cyanobacteria. You guys probably heard of blue-green algae. These are all capable of making ammonium compounds that can be absorbed by plants. The second group, I've heard of rhizobia bacteria. I also found Frankia bacteria. These are found in root nodules of different types of plants. The Frankia is not very common, but the rhizobia are found mainly in root nodules on legumes. So I have some root nodules for your enjoyment. I just really like this picture because here we have our little microorganism breaking up the nitrogen making ammonia. But wherever these are present, the plants that grow in the same soil can take up these ammonium compounds that are made. This is kind of down in the corner. Lightning does a little bit of nitrogen fixation. It's the high temperature of that lightning flash that breaks the bond, and it can react with oxygen in the air, and it makes nitrogen oxides, which combine with water, and they can fall to the earth in the form of nitrates. Not a whole lot of nitrogen fixation that way. You guys will like this. I can't call these islands what I really want to call them, but you'll figure it out. There were some major natural deposits of fixed nitrogen. One of them was the Chinchas Islands, 13 miles off the southwest coast of Peru. And these were basically mountains of guano. And if you know what guano is, well, if you don't know what guano is bird poop. It's seabird excrement. But it's very rich in nitrogen, phosphorus, and potassium. It was the perfect fertilizer. Ships were just, oh, this is a good story. Although, way back in the day, the Incan rulers were so protective of their guano and their seabirds that disturbing a seabird was punishable by death. But from what I remember about the Incas, they didn't have so much of a problem putting people to death. Maybe I'm confused on my theory there, but anyway, from the 1840s to the 1870s, stench aside, ships would line up to get their holds filled with guano. And it was like hell on these islands. They had Chinese laborers and prisoners basically digging guano and shoveling it into ships. And the sailors who sailed these ships, apparently they were very rowdy. Drug abuse and alcohol abuse was really, really high among this group because they're sailing in a ship full of guano. Anyway, there was even a war fought over these islands. But by 18... fighting over shit. By 1874, these islands were stripped bare, so no more guano. The other major deposit that people could get to was the Atacama Desert, and it was a source of Chilean saltpeter, or sodium nitrate, or I think it's also called caliche, if I'm saying that right. Sodium nitrate is inferior to true saltpeter, which is potassium nitrate, but it can be converted, sodium nitrate can be converted to fertilizers. So valuable was this white gold that 3 countries went to war over this region, Chile, Peru, and Bolivia, but Chile ended up getting most of the disputed territory. For more than a century, basically the whole supply of sodium nitrate was mined out of this, or taken from this Atacama Desert region. In 1900, 2/3 of all fertilizers originated in this Chilean saltpeter. This trade wasn't ended so much by a shortage as it was by the emergence of a replacement, one that was more assured, and particularly for countries that didn't have vast natural resources or a dominant navy, so they could make sure the shipments stayed safe, and it could be scaled up to meet the exploding demand for nitrogenous fertilizer. You know what it was? Can you guess? It was the Haber-Bosch process. We know the challenge. Create synthetic fertilizer by the ton to feed the planet. The solution was to try to take atmospheric nitrogen, combine it with hydrogen to form ammonia. This also releases heat. And we had to do this in a cost-effective manner. If it was too expensive to produce, that doesn't work, right? So the great scientific minds of the day heeded Crookes' call to action. Among them was Fritz Haber. Building on the work of greats like Wilhelm Ostwald, he was the inventor of the Ostwald process that converts ammonia to nitric acid. Wouldn't you love to have a process named after you? Right? Don't think that'll happen for me, but maybe for you. Haber threw himself into this nitrogen problem, and in 1908 he started to have some success. It wasn't easy, but the thing you have to realize too is, like I said, thermally, we need temperatures of 1,000 degrees Celsius to break this guy up. But ammonia is as fragile as nitrogen is tough. So any ammonia that dared to form in this reactor would break apart. And there's a thermodynamic equilibrium thing where the hotter it goes, the lower your ammonia, lower your yield of ammonia. So we have to come up with a different solution. Haber waded into the field of high pressure chemistry. Even at high pressures, the yield of ammonia wasn't high enough. So if it didn't work on the lab bench, no point in scaling it up. But there was one more thing he could try. Anybody know what it is? Catalyst, right? Effective catalyst meant both chemically and economically. A catalyst is a substance that helps the reaction along that isn't consumed itself. Haber tried quite a number of them, but finally found that osmium metal worked very well with the uranium, a good second, good second choice. By 1909, Haber and his assistant, Robert Larossignol, had optimized their reaction system. They dialed in the right pressures, temperatures, and catalysts, and they even devised these gas reheating and recirculating systems to make the process more appealing. So here's a picture of Haber and his deceptively simple reaction chamber. July 1909, representatives from BASF one of the, maybe the largest chemical company of the time, came to Haber's lab to see a demonstration. Among them was Carl Bosch. The things were in chaos. His reactor had a leak, so I can't even imagine that, something like that. Bosch actually left in disgust, but his assistant, Alvin Mintosh, stayed. He waited for Haber to get things working again, and lo and behold, ammonia, they condensed it out. Liquid ammonia started running out of the system at a rate of 2 cups an hour. That doesn't sound like much, but before it was like little drips. 2 cups in an hour. Thankfully, Mintosh persuaded Bosch to support the process, and BASF snapped the patents right up. Ironically, BASF assigned Carl Bosch the task of scaling this up, translating it from the lab bench to tons of ammonia per day. Anybody who has baked a cake, maybe it's just the way I bake cakes, you know a little something about scaling things up. I can bake perfect little cakes in tiny muffin tins, and then I put it in a big, like 13 by 9 pan, and the edges get all burnt before the middle gets warm. It's a really weak example, but at least it's something familiar to us. But we're not talking cakes. Bosch was looking at temperatures on the order of 500 to 600 degrees Celsius. That's 900 to 1100 degrees Fahrenheit. That's hot. It's enough to make iron metal glow red hot. The pressures were the more problematic thing, because we're looking at 100 to 200 atmospheres. That's 100 to 200 times what you're feeling right now. It's like 20 times the pressure in a steam locomotive. It's about the pressure you feel a mile down in the ocean. And this is a lame example too, but has anybody ever seen a pressure cooker? I received a pressure cooker as a wedding gift. I promptly went, ah, and passed it along. I did not want this pressure cooker to be in my kitchen with the possibility of going, now, we're going to take our pressure cooker and we're going to make it giant. So that's a little scary. Bosch's system also required the largest compressors in the world, the largest. He had to devise new gas delivery systems. He had to get new valves, new fittings, new measuring devices, everything, totally new from scratch. There were even new types of steel developed for this particular process. It was amazing, right? Totally from scratch. That catalyst reared its ugly head again. There was a problem. There was not enough osmium metal on the planet to fuel the industrial level production of ammonia. Osmium is one of the, I'll put up a more sophisticated looking thing here. Osmium is one of the least abundant metals in the Earth's crust. It's present at about 50 parts per trillion. BASF at the time actually bought the world's supply of osmium. It was 100 kilograms, and that sounds like a lot, but again, we're talking tons, right? So, not going to do it. And I don't think uranium is any better. There's now, take your pressure cooker, pack it with uranium, exploding takes on a whole new meaning there. So, I wouldn't want that in my factory. Chemists came to the rescue again. Good old Alvin Mintosh, the guy who convinced Bosch to do this, he did a whole bunch of experiments. There was like shrapnel in the walls of his lab. But he came up with a great catalyst. It was just a form of activated iron. They're looking for new catalysts today, but they still use Mintosh's catalyst 101 years later. I mean, that is incredible. He actually ran over 20,000 experiments trying to find a better catalyst, and he never did. 20,000. I think that's pretty incredible. Some of you may like energy diagrams, and if you don't like energy diagrams, you do like walking downhill versus up, right? We all found that out walking up to this room. So if you look at the energetics of an uncatalyzed reaction, taking nitrogen and hydrogen, breaking all the atoms up, and going to ammonia, That's a really high growth line. That is not easy to do. You do this on the surface of the catalyst, notice the highest energy thing on the uncatalyzed path is actually the lowest energy thing when you use the catalyst. So, I don't know, I think it's kind of amazing. It's a story of chemistry. Okay. Bosch's first attempts at building a reactor, he had reaction chambers over 8 feet tall. They had walls an inch thick of the highest quality steel available, actually from Krupp's, who was known for making cannons. And he wrapped it in reinforced concrete. Inch thick walls, they burst after 3 days. 3 days. He tried construction after construction, and they kept bursting over and over and over again. So, being the chemist that he was an expert in metallurgy. So he looked at the steel and he realized that the high pressure hydrogen was actually eating some of the atoms out of his steel. So he had to devise, this is an engineering feat, he actually came up with this really neat double wall reactor thing, where it sort of had a sacrificial inner lining and then high strength steel on the outside, and it was perforated with Bosch holes. Bosch holes. But if you think about it, we have nitrogen, which is very unreactive, but then we have hydrogen in our reactor. So think if you had a hydrogen lake in a factory where you have open flames heating gases. Not good, right? But these little Bosch holes would let the hydrogen escape and so that it never built up in concentration, and these worked. I think that's cool. And now instead of, he does have a process named after him, but he also has holes named after him. That's the problems posed by the materials and the related safety issues actually resulted in the chemical industry's first materials testing lab. They opened in 1912, the first one. They were tasked with identifying and resolving problems that arose with the materials used for both process engineering and instrumentation. Now, there are labs that test everything, right? This was new back then. This was innovative. Eventually, Bosch worked through all the problems with his team, and you gotta realize too, this is very tightly integrated. So if something breaks down over here, the whole process gets shut down. So everything had to work perfectly 24 hours a day, 7 days a week, at high temperature and pressure. It's amazing. Now, when I think about having to develop this process, I would think, oh, this is gonna take a decade, 2 decades, more decades, right? They were ready to go in 16 months. 16 months. The plants at Oppau by Ludwigshafen opened, let's see here, in 1913. Their initial capacity was about 20 tons of ammonia per day. That's about 70 to 100 tons of, metric tons of ammonia per year. Now, I can't think metric tons. It's about 16 million pounds. 16 million pounds of ammonia. That was all processed into about 36,000 metric tons, or almost 80 million pounds of ammonium sulfate fertilizer. Bosch had another idea. He didn't want his fertilizers misused. He wanted everybody to know how to use them. So in 1914, they opened the Agricultural Research Station at Ludwigshafen, dedicated to studying soil, fertilizer, and plant physiology. Now we expect everything we use, right, to be thoroughly tested. This was new back then, so I think that's pretty incredible. As big as this plant was, a bigger one opened in 1917. Capacity initially doubled that of the other facility, and it saw expansion after expansion through the next couple of decades. It actually covered 3 square miles by 1944. One chemical plant. That's big. Today there are, let's see, I have another picture of Luna here. It's called Luna. There's another picture of it. These are all historical ones. Today there are 2 plants at Ludwigshafen. The other plant at Luna has been broken up and does different things now. But there are 2 plants still at Ludwigshafen, the Oppau area, still Together, they produce over 2,000 metric tons of ammonia per day. That's an annual output of 730,000 metric tons of ammonia per year, or 1.6 billion pounds. 1.6 billion. Just at these two factories. There are Haber-Bosch plants all over the world. So we're making lots of ammonia. And this is 101 years after they first did this. That kind of staying power is incredible, right? The Haber-Bosch process was really the first foray into high-pressure technology, and it paved the way for a lot of other large-scale chemical processes. In 1922, there was the first industrial plant capable of synthesizing urea, another fertilizer, from ammonia and carbon dioxide at high pressure. It's actually called the Bosch-Meiser process, another process. 1923, Tosh and one of his colleagues developed a method to take synthesis gas, which is a mixture of hydrogen, carbon dioxide, and at high pressure, extreme conditions really turn it into methanol. So based on Bosch's engineering, now we have other compounds we can make. Fritz Haber was awarded the Nobel Prize in Chemistry in 1918. He received it in 1919 for his synthesis of ammonia from its elements. Carl Bosch received the Nobel Prize in Chemistry in 1931 for his invention and developments of high-pressure chemical methods, basically for overcoming the chemical and engineering problems related to continuous flow, large-scale, high-pressure, high-temperature synthesis. Bosch actually shared his prize with another guy, but it was all high-temperature, high-pressure stuff. And with Bosch's, it was very much applied chemistry, right? That doesn't happen so often for Nobel Prizes in chemistry. So he's kind of unique that way. There are a few others, but more recently, the publication Nature, you guys have heard of Nature? In 1999, they named Bosch and Haber the most influential people of the 20th century. The most. That's above Einstein and his theory of general relativity. That's above Alexander Fleming and his discovery of penicillin. Over 200 years, 1800s, 1900s, the Haber-Bosch process was probably only rivaled in terms of its impact on all of humanity by the germ theory of Pasteur and Koch. That was in the 1870s. Okay. Today, more than 140 million metric tons of ammonia is produced by the Haber-Bosch process. That's on the order of 310 million pounds. They can be processed into 450 to 500 million metric tons of nitrogen-based fertilizer. That's almost 1 trillion pounds of fertilizer from the Haber-Bosch process. All the factories combined, or all the plants combined, consume 3 to 5% of the world's methane supply, and 1 to 2% of the world's total energy supply. Total. World production of cereal crops has increased 7-fold over the 1900s. There have been other advances in agriculture, like pesticides and new crop varieties, but all those would have been limited on their impact if there hadn't been a simultaneous increase in the amount of fixed nitrogen available. Oh, I forgot. Anyway, I'll show my high pressure, high temperature demonstration. Should I do it now? Everybody's kind of zoning out, so, well, maybe not. If you've seen this demonstration, please don't give away the surprise. Safety first. I should have pants on, but I don't do pants. So very difficult. Tongs and the lighter, there's nothing to do. Stop it. Probably shouldn't do it right next to my Class dies. It would really be a last lecture now. But not just for me. Okay. So I have a clear colorless liquid in here. Oh, we should turn off the lights.
Do you want me to turn off the light?
Can we dim the lights for a second?
Yeah.
Oh, gotta get my tongs. First time I did this, I nearly burned my eyebrows off. So.
Is that good?
Yeah, that's good. You guys ready? Yeah. Loud, high temperature, high pressure. Now imagine that in reactors that are like 20 meters tall. Bosch is a bold dude. I'd do this again, but it's consumed all the oxygen in here. So I have methanol in here. The vapor reacts explosively once we overcome the activation energy, and you can. So it's always fun. That's the power of chemistry. Explosion. Okay. These two men, Haber and Bosch, actually enabled a population explosion. There were 1.6 billion people on the planet in 1900. Now, like I said, there are over 7.3 billion. Thankfully, we're still going strong. On a more personal level, around half of the nitrogen atoms in your body have been through the Haber-Bosch process. Kind of cool. I mentioned the power of intention when I began. Haber and Bosch intended to develop an economical way to create ammonia from air to create fertilizers to feed people. Tragically, this makes me very sad, so excuse me if I tear up. Their process was hijacked during times of war to produce explosives, and it led to the injury or death of many people, millions of people. Haber once said, during peacetime, a scientist belongs to the world, but during wartime, he belongs to his country. Haber and Bosch were extraordinary guys, but I don't know, their invention was taken over by some not nice individuals. Those two themselves, they were very complex, very human people. I'd encourage you to read about them sometime. It says, this is my last lecture. I'm choosing to focus on the benefits related to the Haber-Bosch process and not dwell on how it was misused by humans. That said, we need to think about the future, what we can do something about. In 1913, Robert K. Merton articulated something we're all familiar with. It's the law of unintended consequences. Any new solution creates new problems that we have to face. It's the same for our ammonia synthesis here. Nature has its own pathway for the uptake and release of nitrogen atoms. But the Haber-Bosch process turbocharged this cycle. The availability of cheap fixed nitrogen has helped feed the population, but it's also affected our environment. Nitrates from fertilized soil, about half of the fertilizer applied to soil actually gets taken up by plants. The rest goes into runoff, into streams. So those nitrates end up in water systems, and this promotes eutrophication. It's algal blooms in rivers, streams, and estuaries. Those algal blooms consume all of the dissolved oxygen, so you end up with dead zones like that in the Mississippi Delta. It's a big problem. Nitrogen also returns to the atmosphere, some of it as unreactive dinitrogen, but some of it as nitrogen oxides. Those compounds, the majority of them are pollutants, components of smog. Nitrous oxide, N2O, is actually a potent greenhouse gas, and it's a precursor to nitrogen monoxide, which catalyzes the decomposition of ozone. So what's left over, those other nitrogen oxides, those can combine with water vapor to form acid rain, or they fall to the earth as nitrates, which run into our streams and rivers. You can see it's kind of a cycle here. We are facing some huge problems, and we need to know more. On this level, we can say, well, how should we use fertilizers and avoid its misuse? Thinking on a bigger scale, what can we do to avoid pollution? How can we reduce climate change? are experiencing that right now. And how do our actions affect the natural machinery of the world? Solutions to these problems may come from multinational teams with thousands of chemists. But we've seen here, it might take just two people to make a difference. Or maybe just one. Maybe one of you will figure out a way to address these things. I find these stories of chemistry to be inspiring, but also calls to action. We can do this stuff. What inspires you? What do you think you can do to make the world a better place? And I have to just put up a thank you to everybody. Thank you for putting up with me tonight. Dean of Students Office, Chemistry Department, everyone at UCSC. This feels like home to me on the way from home today. My mom's Randa Roland. My mom, and I wish my dad was here, but he had Alzheimer's, so I expect one of you to fix that problem. Ron Nelson of Eastern Street too. And of course, Fritz Haber and Carl Bosch. So thank you for letting me talk about this story. I'm happy to answer questions, but I'm also going to be looking at my liquid nitrogen while we're doing that. Any questions?
So I can do questions while she does the nitrogen. We can all kind of coalesce in the area and just check out the nitrogen. I don't know what the safest way to do that is. I want to express my own thanks real quick, and these thanks of the Dean of Students Office and everybody for accepting our invitation, coming, speaking with us. I'd like to present you with this little plaque. And just thank you so much for coming out.
Let's see, if nothing else, I'm listening. You guys can ask questions. You can ask anything you want. You can ask him questions like, how does he live with me? Does he worry about dinner? I think he has written down somewhere that if anything ever happens to him, do a talk straight. Let's see. My doer had to live, so we still have some. So, that was awesome. I should have gloves on. But no, really. Do you guys have any questions? Yeah, Nina.
What got you to chemistry?
I'm a weird person. I took high school chemistry and I just thought it was the best thing ever. It made sense. I wanted to study it. I started seeing the world the way I do. And I never really deviated. And I know that path. Well, I was a poli-sci major for one semester because there's a really cute professor. But then I realized I was never going to be president. So I went back to chemistry and I never looked back. Everybody finds that subject, right, that you just love. For me, it was chemistry. My mom has a BS in biology. My dad was a chemist. He had a master's in chemistry. But they never talked about science, never pressured any of this. But I can't open the tongue exam. Any other? I have glow sticks too. I was hoping they'd go dim or something in the nitrogen, but we don't have to play with those. We can, but we can turn the camera off. Other questions? Yeah.
What do you think is another modern problem that could be possibly solved by chemistry or through the ingenuity of chemists?
Water. I think that's the next big challenge. In developing areas, we know there's a problem with water purity, and there's droughts and floods and everything like that. But for places like California, it does do. For places like California, we need to increase our water supply, and I don't think just conservation methods are going to do it. I mean, sorry, I don't like to be political. Yeah, dim down a little bit. I wanted to bring in like food coloring and see if I could make little drops. Do some molecular gas scrubbing. probably not gonna happen. Yeah, it didn't know quite a bit. Other questions? Yeah.
It's more of like a less chemistry, but when you find that catalyst that you know is going to work and that you know in your life this is going to be the thing, how do you keep reminding yourself that this is going to pay off in the long run, even when you know that like the reactors are blowing up and you don't have Bosch holes and all those things? Like, how do you personally? What's the one thing that keeps you on track and keeps you moving forward?
I think it's just that. For me, it turns into, this sounds weird, it turns into your baby, right? And you will not give up on this process because you know you can make it work, and you will make it work. Bosch actually had a really hard time letting go, and he was kind of forced out when he saw things not going the right way. And he was holding on because he wanted his plant to run, to work. But he died an alcoholic, so. I think it's just that passion you have for it, and it's just you know, and you won't give up. And when you find it, you won't give up. I mean, Rebecca is a research scientist, and I'm sure things do not always work.
Most of the time they don't.
But you keep trying. Yeah. You know there's a way to solve the problem.
And it's sweet when it does work.
Yeah, it's a total high. It's a rush. And honestly, with some things, I think just showing up every day, you show up and you try, and you get to where you're going.
Or you find something you didn't expect that's even better or different.
Right. But showing up is half the battle. Don't give up on that. Yeah.
Was it true that Haber actually voluntarily offered his method to the German government to reduce?
It wasn't so much voluntary as it was they were going to take it, because all this development costs a lot of money, and they were fairly dependent on the government to supply them with all that money. And you can't have, you've got to scratch backs both ways. Haber was actually, he had to leave the country. He was a Jew, and he was forced to leave. It's a sad story. He died on his way actually trying to get to Israel and go to a chemical institute there. And Bosch saw his baby getting taken over for purposes he didn't agree with. And I think we all don't agree with the purposes of the government at that time there. And like I said, he got shoved out kind of, or exited, and turned into a raging alcoholic. It destroyed them to lose their process and to see what happened to them. So again, focusing on the good now, because I think that tragedy just can't be minimized. Other questions? Oh, yeah.
Why did you choose to teach rather than join a large chemical institute or something like that?
I worked in industry for a while over the hill, and it's its own kind of high. But I found it to be very solitary, and I enjoyed trying to figure out new ways of doing things, but it wasn't as alive as teaching. And then part of it too is there aren't a lot of jobs on this side of the hill. So I started teaching at Cabrillo and was like, this is awesome. And then I came at the right time here and started teaching here, and this is amazing. I love this job. And it's you guys, I mean, UCSC is a really special place. So, and I just like talking about chemistry to people. And hopefully it makes it bearable, if not enjoyable. Yeah.
Besides the cure for Alzheimer's, what do you see in terms of the long-term future of chemistry in society?
We're going to keep pushing limits. I mean, think about nanotechnology, quantum computing, water, biomedical research. We have staggering problems now. The health of humanity, the health of the planet, that's all chemistry. So that's where we need to be looking in my group. I mean, kind of you can look at anything and see problems with it, but you can also take good things and make them better. More cost effective, more widely available. But everything around us, math and energy, is chemistry. That's part of the reason I like it.
Can I add to that? I mean, in terms of a grassroots level, do you think we'll have some kind of, or how soon do you think we'll have an energy crisis involving gasoline prices and, just or the fuel in terms of everything?
I would hate to guess on that, just because it's so politically charged. I mean, I think solar power is the way to go. I think it's an amazing technology that really needs to be investigated further, because we haven't, we've barely scratched the surface on the materials we can use to do it. And water splitting, catalysts for that, I think those things really need support and smart minds. So, yeah. Did I answer the question?
Yeah, that's good, thank you.
Okay. Other questions?
I have a suggestion for your beer.
Oh,
What's that? You should, instead of trying to make beer, you should just make beersicles.
that was good. Talking about those little capsules, yeah, like Dippin'
I've seen
Dots
like
out of beer.
popsicles.
Yeah. Some of you are under 21 though, so we're like corrupted and you can't.
You could get alcohol-free beer for them.
Okay. Yeah, that's what we'll do. The tattoos are bad enough. I can just see people going back, Mom, Dad, my chemistry instructor has all these tattoos. And it's like, great. Other questions? Thank you very much for coming out tonight.
Let's go.
Excellent.